Our next unit of study is going to involve imaginary numbers, and I want to start just by reading an article found on the Khan Academy website. It's called Intro to the Imaginary Numbers. I'm just going to read over this and you can read along with me. In your study of mathematics, you may have noticed that some quadratic equations do not have any real number solutions. For example, try as you may, you will never be able to find a real number solution to the equation x squared equals -1. This is because it is impossible to square a real number and get a negative number. Remember that a negative times a negative would always be a positive, so there's no real number that I can plug in here for x, where after I square it, I'm able to get any negative number, let alone -1 specifically. However, a solution to the equation x squared equals -1 does exist in a new number system called the complex number system. So if you think back through the number systems that you've learned about, you've learned about rational numbers, and that's where you have any integer divided by another integer. And then you've expanded upon that and learned about something called irrational numbers, where you might have a decimal that never repeats or never ends. And when you put all those rational and irrational numbers together, then you're dealing with real numbers, stuff that you can plot on the real number line. Well, this kind of expands upon that. Your complex number system is going to include all those real numbers plus this new idea of the imaginary number. The imaginary unit. The backbone of this new number system is the imaginary unit, or the number I. The following is true of the number I. I is equal to the square root of -1, and if you square that, you'll have that I squared is equal to -1. The second property shows us that the number I is indeed a solution to the equation x squared equals -1. Notice that if you plug in the square root of -1 in place of x here, and then if you square a square root, those are inverse or opposite operations, the only thing you would be left with would be this -1 here. The previously unsolvable equation is now solvable with the addition of the imaginary unit. Pure imaginary numbers. The number I is by no means alone. By taking multiples of this imaginary unit, we can create infinitely many more pure imaginary numbers. For example, 3i, I root 5, and -12i are all examples of pure imaginary numbers, or numbers of the form bi, where b is a non-zero real number. Taking the squares of these numbers sheds some light on how they relate to the real numbers. Let's investigate this by squaring the number 3i. The properties of integer exponents remain the same, so we can square 3i just as we'd imagine. So 3i, that quantity squared, kind of distribute this squared here, so it's 3 squared times I squared. The 3 squared part would be +9, and then you have 9i squared. Using the fact that I squared is equal to -1, we can simplify this further as shown. 9i squared is the same thing as 9 times -1, which equals -9. And I just want to take a moment here and point out this substitution because it is a very important one. You are going to be doing this many, many times. So take a note and write I squared is equal to -1, and always look for places to make that substitution when you're working with these imaginary numbers. The fact that 3i squared equals -9 means that 3i is a square root of -9. In other words, if you take the square root of -9, actually here, let's write that. So if I do the square root of -9, that answer would be 3i. And if you find that confusing, here's another way to kind of view this. Think of this square root of -9 as 9 times -1, and the square root of 9 this piece of it will give me 3. And the square root of -1, this piece of it, will give me I. All right, let me clear that out. So let's check our understanding. Check your understanding. What is 4i squared? So if we're doing the quantity 4i squared, we're going to do 4i times 4i. So we should be thinking, okay, that's 16i squared. Remember that the I squared is -1. 16 times -1 would give me -16. Which of the following is a square root of -16? So if I take the square root of -16, and here's another thing you just kind of want to get used to. As soon as you see this negative underneath the square root, think of that as I, because this negative is like a -1. Square root of -1 is I. So immediately, as soon as you see a negative under there, turn that into an I. And the other piece of this, the square root of 16, that's of course just going to be 4. So my final answer should be 4i. All right, let me clear that out. In this way, we can see that pure imaginary numbers are the square roots of negative numbers. Simplifying pure imaginary numbers. The table below shows examples of pure imaginary numbers in both unsimplified and in simplified form. So in unsimplified form, we have the square root of -9. Simplified form, that's just 3i. Unsimplified form, square root of -5. There's that negative. Imagine just kind of pulling that out, and you have I root 5. You cannot simplify the square root of 5. The opposite, or negative root of -144. So here, let's color code the parts of this. So this negative sign is right here. And you have this negative underneath the square root symbol. Think of that as a -1. The square root of -1 would be I. So that's that piece right there. And you have this 144 underneath the radical. The root of 144 would just be 12. So the opposite of the root of -144 would be -12i. But just how do we simplify these pure imaginary numbers? Let's take a closer look at the first example and see if we can think through the simplification. So the original equivalence, the root of -9 was 3i. Thought process. The square root of -9 is an imaginary number. The square root of 9 is 3, so the square root of -9 is 3 imaginary units, or 3i. The following property explains the above thought process in mathematical terms. So for any a value bigger than 0, if we take the square root of the opposite of a, we're going to get I times the root of a. Once again, notice I have that root, or the negative sign underneath this radical. The square root of -1 is I. And this a, the root of a, is just the root of a. If we put this together with what we already know about simplifying radicals, we can simplify all pure imaginary numbers. Let's look at an example. So in this one here, we have simplify the square root of -18. And I'm just going to kind of talk you through this. So the square root of -18. So right away, let me deal with this negative sign. So the square root of -1 is I. So I can look at this as I times the root of 18. Now I need to remember how to simplify this root of 18. And when you think of 18, think of that in factored form as 9 times 2. And the advantage there is that we can now root the 9. The square root of 9 would just be 3. And this root 2 we can't do anything with. And just to make this look a little cleaner, we can write this as 3i root 2. And this is how I want you to write this. Another acceptable answer, and this is probably more common actually, is to write 3 root 2i. But the problem I have with this is that sometimes students are a little sloppy with the radical, and they'll extend it a little bit further, and it'll look like their I is underneath the radical symbol. And we do not want this I to be underneath this radical symbol. We want it to be on the outside. So just to kind of guarantee that that doesn't happen, just write it like this 3i root 2. And then with simplifying the root of 18, the other way you could think of this is to just kind of break this down. So, think of two numbers that multiply together to give you 18. That's 3 times 6. 6 is the same thing as 2 times 3. So when you're dealing with root 18, you're really dealing with the root of 2 times 3 times 3. And anytime you take the square root of 3 times 3, it's just going to be one of those factors in front of the radical. So this 3 times 3 is 9. Square root of 9 is just 3. And the 2 is kind of stuck under there. You can't pull that out from underneath the radical. Okay, so moving on. So here's the Khan Academy explanation. First, let's notice that root negative 18 is an imaginary number since it is the square root of a negative number. So we can start by rewriting root 8. The root of negative 18 is I root 18. Next, we can simplify root 18 using what we already know about simplifying radicals. The work is shown below, and we pretty much have already explained all of this stuff. All right, so moving on, let's practice some problems. So the root of negative 25, well, this negative is an I, the root of 25 is 5, so this one here is just going to be 5I. Number 2, the root of negative 10, this negative will just be I. Can I simplify root 10? And the answer is no. 10 is just 2 times 5. I don't have 2 of the same factor multiplied together underneath the radical. I don't have a perfect square number that evenly divides 10. So the best I can do with this is I root 10 or root 10 times I. Let's see how they wrote it. So they wrote I root 10 there or root 10I. They actually have both answers there. The root of negative 24. All right, so let's work this one out here. So if I have the root of negative 24, that's the same thing as I times the root of 24. When you think of 24, let's do the factor tree real quick here. 24 is 12 times 2. 2 is prime. 12 is 4 times 3. And this 4 is 2 times 2. So 24 is really 2 times 2 times 2 times 3. So we have I, 2, 2, 2, and 3. So when we take this square root, this is really a 4 right here. We can take the square root of 2 times 2 or the square root of 4. That's just going to be 2. And we'll just bring this I down. And we can't do anything with this 2 times 3. So our final answer is just going to be 2I root 6. So my largest perfect square number that evenly divides 24 would be 4. So the other way to write this, to break this up, is you can write this as 4 times 6. Take the square root of 4, which is that 2. And the 6 is kind of stuck under there. And let's write that in here. So it's 2I root 6. So 2I, and we got square root 6. Check. Why do we have imaginary numbers anyway? The answer is simple. The imaginary unit I allows us to find solutions to many equations that do not have real number solutions. This may seem weird, but it is actually very common for equations to be unsolvable in one number system, but solvable in another, more general number system. Here are some examples with which you might be more familiar. With only the counting numbers, we can't solve x plus 8 equals 1. We need the integers for this. So the solution to this, it would be negative 7 plus 8 equals 1. And if you don't know that negatives exist, if you don't know that integers exist, you would say that this equation has no solution. But it does. Negative 7 plus 8 would equal positive 1. With only the integers, we can't solve 3x minus 1 equals 0. We need the rational numbers for this. So there is no integer that I can substitute in for x to solve this. The solution to this, if you add 1, divide by 3, solution to this would be 1/3. That's 1/3 is a rational number. And if you didn't know that those kind of numbers existed, you would say, oh, there is no value for x that will work for this equation. But that's not true with rational numbers included. With only the rational numbers, we can't solve x squared equals 2. The correct answer to this would be the square root of 2, and that's an irrational number. Enter the irrational numbers in the real number system. So we're just expanding this one step further, and so with only the real numbers, we can't solve x squared equals negative 1. We need the imaginary numbers for this, As you continue to study mathematics, you will begin to see the importance of these numbers.